my students. I'm going to try this again. I actually just did the whole lecture and then realized that I wasn't recording, so I might occasionally check up here to see if I am recording. That red circle up in the top right corner means that I'm recording. That's a good sign. All right, so welcome to Rocks in Mineralogy. I'm going to take you through this course in a different way than I have taken any other students through it before, especially because I can't be there in person. But I think you're going to be able to do this. This is going to happen, and you will graduate. But like I said in the other video, you'll have to work together and work hard. Ask me questions. Please ask me lots of questions so that I can help you. All right? Okay. I'm going to start off with the Earth's inner systems, with Earth's history and structure. By the end of this lecture, you'll be able to explain the basic history of Earth's formation, starting with the creation of elements, all the way to the creation of the planet. You'll be able to explain to me why the Earth was hot enough to melt, and explain to me how the Earth started to cool and is still cooling now. You'll be able to explain to me the reason that the Earth is stratified. We'll look at that in a little bit, but think about your roots, stratified. You'll be able to draw and label the chemical layers of the Earth and the mechanical physical layers of the Earth. When I say in this class mechanical or physical, they mean the same thing. So sometimes I might say mechanical, sometimes I might say physical. They mean the same thing. You'll be able to explain how the chemical layers of the Earth and the mechanical layers of the Earth are related to one another. And you'll be able to tell me the 8 most abundant elements in the Earth's crust in order. You've done this before in geology class. And you'll be able to explain to me why they're the most abundant, more abundant than all the other elements in the Earth's crust. All right, so we're going to start at the very beginning, which is, in this scenario, is the theory of the Big Bang. All right, so here we've got the Big Bang, the very beginning. And some of you might know I am what we call an old Earth creationist geologist. That means I do believe that the universe and the Earth were created out of the Big Bang and developed to what it is now. I don't think they happened like that all on their own, but I do believe that it did happen over a slow process. In this class, we don't really care about this first 300,000 years, but we do care about the creation of the elements and the atoms, which happened in stars, the very first stars, and we've had more stars created since then, which turned into galaxies and solar systems, and this is where our Earth is created in this time in here. So how did that happen? Well, after the Big Bang, we end up with just a whole bunch of hydrogen atoms. Maybe a little bit of some other things, but mostly just hydrogen atoms. And these hydrogen atoms were out in space, but anything with mass in hydrogen, one hydrogen atom has mass, will pull itself towards anything else with mass. So 2 hydrogens will pull each other towards one another through their own gravity. So gravity started pulling groups of the atoms together, and as they came closer, they became clouds of gas. We've got gas. Gas is anytime we've got elements that are close together and they're able to bounce off of each other, but they're far enough apart to not make a liquid or a solid, right? And these clouds were called nebula. So this right here is a nebula. As these elements started getting closer and closer together, they're being pulled together by gravity. The pressure is increasing, and the temperature is increasing. And the high pressure and temperature at the center of this nebula, hot, 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 and high, high pressure, started nuclear fusion. And at this point, all of this gas becomes a star. And the hydrogen gas, we've got hydrogen gas and hydrogen gas, and this nuclear process, this nuclear fusion, is combining hydrogens to make helium. So hydrogen is going in and helium is being created inside of the star. If the star started with a very large cloud of hydrogen, if it started with a large nebulous, then it will make a very large star, and that star will be able to create elements up to the atomic mass of iron. And at that point, in the periodic table, it will stop. It won't make any elements that are higher density or higher mass than iron. As the star goes from making hydrogen to helium and all the way through the elements to iron, it starts to run out of its fuel. The hydrogen and then the helium in each of these becomes fuel. But it cannot burn its iron. Iron is too dense, too high, takes too much energy to burn through nuclear fusion. So as the star starts to run out of these low density elements, it collapses, the star collapsed on itself, and then after that collapse, it exploded as a supernova. So this over here is a picture of a supernova. So the star, the star collapses, and then all of a sudden explodes with great force out into the universe. When it does that, that explosion is called a supernova. The power of that supernova, that explosion, creates all of the rest of the elements in the universe. And the death of one star can create many different elements. And that supernova explosion pushes those elements out into the universe. Give me just a second. I'm going to have some alarms going off if I don't do something about it. All right. So we're spreading all of these elements out into the universe. And they spread out. They don't just spread out straight away. They spread out in swirling eddies, turning eddies. So just like you've seen water go down a drain, that's what's happening here. It's swirling out like this, swirling eddies. And these elements get closer and closer together, becoming minerals, and then rocks, and then planets. So this is the creation of the elements, right? The elements are being created in the death of a star, and they're being pushed out into the universe in swirling eddies. From that point, we can start to talk about the formation of the Earth. We could talk about the formation of the solar system. I'm going to skip that. But as these swirling eddies are going, we do get a new star. That's our sun. And gravity is also going to create a pull to pull together these minerals into rocky planets. So minerals are pulling together to make rocks in space. And you'll be able to see that in the video that I sent from YouTube. It's a great example of what happened there with the salt grains coming close together. It's very interesting. Then as the rocks get higher amounts of mass, their gravities are pulling them together and pulling them all into a planet. Right? So all these rocks are getting pulled together because of their own gravity, and that rock is getting larger and larger and larger until it becomes Earth. And that's really what Earth looked like back then. Earth, there we go. There's a hot melted ball of elements. And over time we've got more meteors that are rocks that are coming out of space. They just keep hitting the Earth. I want to remind you at this point that Earth is an open system. And what do I mean when I say open system? I mean that energy can be added to the Earth. Energy can be removed. Energy can be removed from the Earth. Energy can be added. It can be added from the sun. But at the beginning, it wasn't really the sun that was creating all of this energy. It was all the rocks that were coming in, all the meteors. So the Earth has always been like that. It's always been open with the ability for energy to come in and for energy to come out. All right. We're going to talk in a little bit about how Earth has physical and chemical layers. And because it has these physical and chemical layers, we know that something must have happened to turn solid rocks into a bunch of melted rock. All of it had to be melted at some point, or we wouldn't have different kinds of layers. So how did the entire planet melt? Right? Now, it happened in two different ways. It happened from the heat of meteors hitting into the Earth, that friction. So we're turning kinetic energy of moving rocks, moving meteors, is being turned into thermal energy when it hits the Earth. We also have a bunch of radioactive elements, a lot of radioactive elements inside of these meteors. And when they become part of the planet, they're going to go through their radioactive processes, degrading and releasing much more energy. So the radioactive elements are increasing the temperature, and this kinetic energy turning into thermal energy is obviously thermal energy is increasing temperature. So Earth started off not as a big rock, but actually as a big hot, melted spinning ball of mixed elements, a bunch of liquid with all these different hot elements inside of it. So what could have happened next? What processes could be involved here? Well, let's look at it. First of all, we're going to have some transfer of energy so we've got a really hot ball of melted elements, probably between 4,000 to 6,000 degrees Celsius. And then we've got this hot ball of elements, Earth, is floating in space, which is negative 450 degrees Celsius or so. Big temperature difference, right? So this hot ball has to become cool over time, right? Just like a hot potato, if you put a hot potato on a table, over time, the potato would become cooler. How would it happen? In the Earth, it happens for three reasons. We've got convection, energy being transferred, heat being transferred because of convection, heat being transferred because of conduction, and heat being transferred because of radiation. And all of these happen in the Earth. So at this point, I'm actually going to pull this closed. Or not closed, I'm just going to do this. I'm going to make sure that I'm going to make sure that this is still happening. How do I make sure? Yes, good. We're still recording. Great. So I'm going to draw these three processes out for you. All right. So the first one we're going to show is convection. And a good way to show convection is if I drew a pot and I put some water in that pot. And then I put a fire under that pot. And I'm going to put some pieces of rice in the pot. All right. And if you've ever looked at pieces of rice in water that's being heated, you'll notice that the pieces of rice start to move in this circle pattern. They'll move up, and then on the inside they'll move up, and on the outside of the pot, you'll start to notice that they're moving down. And they keep doing that. They go up, and they go down, and they go up, and they go down, and they make these circles. And these are convection currents. And the same process is happening inside of the Earth. I'm going to draw the Earth now. Here's our planet. Inside of our planet, we're going to talk about these layers a little bit later, but we've got a core, and it's very hot. And then above that core, we've got a liquid layer of the mantle. So this is liquid. And the mantle, sorry, not mantle-y, mantle. And the liquid mantle, we've got that heat on the inside, just like we had the heat from the fire. And that mantle is going to do the exact same thing, where we've got places where hot liquid mantle is moving up. And then we've got places where cooler liquid mantle is moving down, and it's going to be these same kinds of circles. Hot mantle moving up. Up meaning away from the center. So even though this looks like it's down, it's away from the center. And cool mantle moving down towards the center. This is happening all over the earth, all through in the inside of the liquid mantle. This is convection. We're moving the heat. Heat is moving from, I'll use yellow for this. Heat is moving from the inside of the earth to the outside of the earth. And so that's because this area is liquid, this is convection. That's how the heat is moving from the inside to where it's going to touch, up here it's going to touch the crust, the outside of the earth. Where's that? Oh. Crust. So now the crust is getting touched by hot liquid mantle because of convection. All right, so that's convection. I'm going to close that one out, and now we're going to talk about conduction. Conduction is what happens when something touches something that's hot, and then that second thing becomes hot. So again, we've got a pot. We've got a fire under that pot. And if you touch that pot with your hand, and you're not careful, if that's not a careful way to touch the pot, then your hot hand is going to get hot, right? Because the heat is going to move from that hot pot into your hand. Ouch, all right? The same thing's happening in the earth. So we've got planet Earth again. Here's our crust, the outside of the earth. Got that mantle, or we've got that core on the inside, and then we've got the yellow mantle. And the yellow mantle, that mantle was, was convecting and getting heat up to this point, right? So now where the mantle touches the crust is getting hot. It's hot right here, and it's just going to move just by touching, the mantle touching the crust is going to get hot. And this is conduction. Now let's make that a little thinner so you can read it. Conduction. This is moving heat further away from the center of the planet to the top of the outside of the planet, right? Right, and then on our last layer, we've got radiation. And radiation happens when energy is moving through a gas or through a vacuum. Actually can move through all sorts of different things, but let's say say this is your window at home, right? And underneath you've got your radiator, and it's hot, right? And then you're just standing near it, and you're not touching it, but you can feel the heat coming off of the radiator. It's radiating, right? The radiator is radiating. You're not touching it, but the heat is affecting you. It's radiating into the room. The same thing happens with the Earth in space. So here we've got the Earth. And I said the Earth started off around 4,000 to 6,000 degrees Celsius. The surface of the Earth, obviously, it's cool enough to stand on. But we've got places where there are volcanoes that come through and such, right? So now we've moved we've moved the heat through convection, through the mantle to the crust of the Earth, and now that heat is going to radiate out into space, because space is a lot colder than the crust of the Earth. It's just moving away, not touching anything, just moving into space and getting lost. So we've gone through 3 stages where the heat was moving from the inside of the Earth. Oops. Inside of the Earth. It's not letting me. I see. There we go. The inside of the Earth to the crust. And then from the crust, or from the mantle into the crust, and then from the crust into space. Convection, conduction, radiation. All right? And there'll be a point in the quizzes where you each have to pick one of these and explain how it works. All right. Moving back over here, and again, I'm going to make sure. There we go. That's where we're at. We're still recording. That's a good thing. All right, so I'll send you those drawings, and that way you'll be able to see each of those. All right, so let's look at what's happening in this video. This is not about temperature. This is going to be about physical layers of the Earth. So let's see here. I'm going to play that for you 2 times here. It goes really fast at the beginning, but the color of the liquid at the beginning is the same, and then it suddenly changes into 2 different colors. What's going on here? Why are the fluids separating? Well, of course, that's oil, and that's water. And why are they separating? Why does oil stay on the top of water? The answer is density. Oil has low density, and water has high density. Basically, that's the reason. All right, so we've got low density oil and high density water. They separate because of their differences of density. Earth did about the same thing. All right, so we've got Earth that's cooling, and we talk about cooling from the beginning using convection, conduction, radiation. And then these layers can happen because of physically because of the way it's cooling, and chemically because of something else. Oh, stratification. I said we were going to get to this. Strata. Strata means layers again, and phi thick. So strata and thick to make. So the Earth is made of layers. All right, so if we look inside the Earth, and we go all the way to the center of the Earth, so this is the inside of the Earth, middle of the Earth, right here at 0 kilometers. And then we look and we compare the density of the Earth from the middle of the Earth all the way up to the outside of the Earth, this being the ocean and the Earth's crust up here where we're standing. We'll see that the density changes dramatically. So at the middle of the Earth, we're going to be inside of the core, and the density is very high. So we've got over 12 grams per cubic centimeter or kilograms per cubic meter for the inner core. And then that density drops when we get to the outer core. It keeps dropping down to about 10 grams per cubic centimeter, and then suddenly it dramatically drops when we get into the mantle. This is a new layer of the Earth. So we've got the core, and then we've got the mantle. These are layers. This is the inside the Earth, and then this is the middle layer, the mantle. And then out here we've got the Earth's crust, And it's very low density. It's anywhere between about 4 and 2.4, right in here, 2.4 kilograms per cubic meter for the Earth's crust, depending if we're talking about oceanic or continental. And then up here we get to the ocean. And what's the density of the ocean? It's made of water. So it's right about 1 gram per cubic centimeter. So the density of the Earth increases when you go from the outside of the Earth, the crust, all the way inside to the core. Oops, wrong direction, Carrie. This means that the Earth is sorted into layers based on density. The density is controlling where those layers are. Let's see this one more time here, where the core is very high density, then the mantle, and then the crust. And then above that, we've got the hydrosphere, right? Oceans are 1, and then the atmosphere. Our air is less dense than water. Water is less dense than rock. And then the Earth's crust, rock, is less dense than the mantle. And the mantle is less dense than the inside of the Earth, the core. That Earth crust right here, it's the part where we stand. It's the rock that we walk on. And it's made mostly, 98.5%, of only 8 elements. Do you remember this? Here we go. This is from geology class. Oh, C. Elphi? Kanak. You remember this? I'm going to throw them all at the same time. You remember what each of these stands for? O is oxygen, silicon, aluminum, and iron for Elphi. Calcium, sodium, and potassium for Kanak, and magnesium for Oh, see Elphi? Kanak. Yes, just to help you remember, because you should know it. So the outside of the Earth's upper layer, is made of these elements, and actually mostly made of oxygen. You're mostly walking on oxygen, and I think that that's very funny. All the other elements in the Earth's crust only make up 1.5% of the crust. And why is that? Let's see here. Well, oxygen, O, C, Elphi, Kanak. There we go. These are all very low density elements. Many of the other elements in here that are even lighter end up being in gases or in our organic material, which is on top of the rock, right? We are organic, and we're made out of things like carbon and nitrogen. We're also made of oxygen and stuff too, right? But hydrogen and water, these things are much lighter. But our OC, Elphi, Kanak, those 8 are pretty light elements. So we call these the rock-forming elements because they make the Earth's crust. OC, where's the aluminum? Elphi, Kanak. And everything else, especially outside of this green area, these are all, you can find all of these other elements in the crust, but they're much lower in comparison. So our atomic number, these are the low density elements on this end, and they're going to become higher and higher density this direction all the way up to uranium, so from hydrogen to uranium. And this is how often do we find them in the crust, right? So these are the ones that we find the most often, and the ones down here are the ones that we find the least often. So I want you to be able to do this. So compare the abundance of less dense and more dense elements in the Earth's crust, which are more common, and why should they be more common? All right, we're going to see this picture a number of times, and I apologize, we're going to get the stratify thing here in just a second, but really, really important for this class that you understand this concept. So take a break for just a minute. I want you to understand this. So get up, stop for a moment, stretch. Let's see if I can get this to, yes, all right. Take just a moment. I want you to stretch. Stretch break. It is so important that you get up, that you move. Move your muscles. Move around. Shake out a little bit. Because I want you to be able to think through the rest of these slides. We're about halfway through. We're about to continue. Ready? 3, 2, 1, and How do I get us to keep going? Now we go. All right. So here we've got the Earth, and it is about 13,000 kilometers in diameter all the way across, right? And inside of that diameter, we've got all these different layers. So 6,000 kilometer radius. And we've got two different types of layers that happen at the same time. We've got chemical layers, and when I say chemical, I want you to think about the rock types. I want you to think about elements, okay? And we've got mechanical layers or physical layers. This is how the rocks move, how they behave. And when we say this, I want you to think about states of matter. All right, so we're going to talk through these concepts. We're going to see this slide 3 times. Again, strata, layer, fix-fi, to make. We're making layers in the Earth, both chemically and mechanically. 2 different types of layers happening together and at the same time. So I've got a question for you. What is the chemical inside of the jar in the picture? What chemical is that? What's in there? Chemical, chemical, chemical. What is it? Of course, it's H2O. All right, so I've got something strange to say to you, and hopefully you can get this. You're going to get this. You ready? Is H2O water? Nope. H2O is not water. I cannot say that all H2O in the entire universe is water, right? But I can say that water is H2O. H2O is not ice. I can't say that all H2O in the entire universe is ice, but I can say that all ice is H2O. Both of these are the same chemical, but they have different states, solid and liquid. I can have the same chemical in more than one state. Right? Okay, Carrie Box, we know that. Good, I'm glad you know it. It's going to be very important. Ready? Here we go. One chemical compound can have many different physical states. So it could be solid, it can be liquid, it could be gas, it could be a plasma. We don't care about plasmas in this class. Don't worry about plasmas. We don't even really care about gases. I'm not going to totally scratch that one out. In this class, mostly we're concerned about solids and liquids and this other strange thing that happens that's in between a solid and liquid, and it's called a plastic. Plastic. This is an interesting idea. We're going to come back around to finding out what a plastic is in a moment. But let's think about solids and liquids. All right. Normally, how do I turn a solid into a liquid? What am I going to do to make that happen? I'm going to add heat, right? If the heat temperature goes up, the solid will become a liquid, most normally. And if it gets even higher, it will become a gas. All right, so this is an interesting problem. What happens if I take a solid? So why is that happening actually? It's happening because the water atoms, water molecules are vibrating faster and faster. So they're vibrating back and forth, right? And in the ice, they're close together. And they're just vibrating, not moving around, right? And then as the heat increases, the temperature increases, they can break apart and move and flow around one another because they have a higher amount of energy, right? So they can flow around. Here they have to stay inside of the ice form. All right, so what happens if I put a lot of pressure on a chemical while I heat it up? So if I've got a solid and I put lots of pressure, but I'm also increasing the temperature. At this point, the atoms inside of this solid are vibrating very fast, but they can't move far apart from one another because of the pressure that's pushing them together. So the atoms move faster, but because they are still pushed close together, they will still be a solid. What, Carrie Box? Yes, you can keep a solid even when it's very hot if it has enough high pressure pushing it together. A chemical can be forced to stay solid even if it is very hot. All right, I'm going to switch back over to this idea of plastic. I should have done these in a different order, but we're just going to go with it. Some chemicals can act even stranger if they're hot and under a lot of pressure. They can sometimes act like a solid and a liquid at the same time. And in this case, we're going to call that, if it's acting like a solid and a liquid at the same time, a plastic. A plastic is going to be a little bit more like a liquid, but sometimes it acts like a solid. Okay? So we can see that in this picture. This is oobleck. This guy is pounding on. When he's pounding on it, he's adding a lot of pressure, and it's going to act like a solid. But over here, you can see the oobleck that's dripping off of his hand. It's acting like a liquid here. And here, it's acting like a solid. Same stuff, but acting in two different states of matter. Very strange, yes. Later in the semester, we're going to learn about a liquid that acts like a gas also, possibly. I think we'll talk about that. All right, so let's look at these layers. So we've got, this is a beautiful picture of the inside of the Earth. And we've got all these different layers. We've got the inner core and the outer core, the mantle, the asthenosphere, and the crust. And those are the pieces that I care about for you. So inner core, outer core, mantle, it's hard to see that, asthenosphere, and crust. All right, so we're going back to this same slide again. Earth has two different types of layers. We've got chemical layers. I'm going to say this multiple times. I want you to think about elements. And mechanical layers. Here I want you to think about states of matter. So we've been talking about both these ideas up above, and we're going to apply them now to the Earth. All right, so the Earth's chemical structure starts off with its crust. This is the very outside of the Earth, between 5 and 60 kilometers thick. We've got two types of crust. We've got continental. That's this taller, thicker piece. That's why sometimes it can be about 60 kilometers. And we've got oceanic crust. This is the crust that's underneath the ocean. The reason why they have different thicknesses is partially dependent on their chemistry again. So the crust, the continental crust, oxygen is its most abundant element, and then silicon, and then aluminum, like OCl, right? The ocean crust, oxygen is the first most abundant element in the oceanic crust, then silicon, and instead of aluminum, now we've got iron and magnesium. This is the chemistry of this layer. The next layer down is between 2,900 and 3,000 kilometers thick. And we've got similar elements, but a different order. So now oxygen is the most abundant still, then magnesium. Magnesium is the second most abundant, then silicon, then iron. So that's the chemistry of the mantle. And then this one's going to be oxygen, silicon, and aluminum. And the oceanic crust is going to be oxygen, silicon, iron, and magnesium. We're going to go down one more layer, and the chemistry is going to change one more time. This chemistry is made only of iron and nickel. All right, so we've got 3 different chemistries. There's other elements in the crust, there's other elements in the mantle, but in the core, we primarily only have iron and nickel. Different elements for different layers. All right, why? Why do we have the elements where they are? It comes down to density again, right? Oxygen, silicon, aluminum. Aluminum is slightly lower density than iron and magnesium. Magnesium is actually higher density than silicon, so when we go down to the next layer, it's getting more dense. Density is increasing. And then we get to iron and nickel, and density is increasing one more time. Remember, rho means density. All right. All right, and then now we're going to look at the mechanical or physical layers of the Earth. This is, again, how is it acting? What is its state of matter? So in the mechanical layers, we've got 5 different layers that are made out of the chemical layers. The lithosphere, it is solid, and it's made out of the chemical crust and out of the very top of the mantle. Then we go down 1 layer, and we're going to change. We're going to be plastic. This is going to be, so this one's solid. This one's going to be more like a liquid plastic. I'm going to write liquid here. The asthenosphere is made out of the upper part of the mantle, so it's chemically made out of mantle, and it's acting like, in the asthenosphere, it's acting like a liquid. We go down 1 more layer. We're still in the chemical mantle. This is the bottom of the mantle, so these are the same chemistry, but now that liquid is acting like a solid. Why is it acting like a solid? We're going to talk about that in just a second. You'd expect that the temperature is getting higher as we go this direction, right? Temperature is increasing. So why would this be solid instead of liquid? All right, then the next layer down, we're going to be in the chemical core, and that chemical core on the outside is liquid. And then you keep going down into the core, and it becomes solid. Same chemistry. These 2 are both iron and nickel, chemically. But the outside of the core is going to be a liquid, and the inside of the core is going to be a solid. What's going on here? Why are we going solid, liquid, solid, right? That's a good question. Oh, wanted to point that out. Lithosphere, lith, over here, lith means rock. So it's the rock sphere, it's the solid rock sphere. If you really want to know, astheno means weak. So a plastic liquid, it's not going to be as strong as a solid. So the asthenosphere is the weak layer, and lithosphere is rock layer. Don't need to know that, that's just for your own knowledge, all right? So here we go, we've got 5 different mechanical physical layers, and we're starting off with a solid on the outside. That's the rock that we're standing on, right? It's the top of the Earth. Then we get to the asthenosphere and the mantle, and these are all the same chemistry. It's mantle chemistry. Mantle chemistry. It starts off with a liquid plastic. It's more like a liquid than a solid, but because it convects. And underneath it becomes more like a solid. Why is it becoming more like a solid? Even though this direction, as we do this, remember, temperature is increasing, right? Temperature is increasing as we go to the inside of the Earth. But at the same time, pressure is increasing. So as the pressure is increasing, we're pushing those elements closer and closer together. Got liquid mantle getting pushed and pushed and pushed closer together because of pressure, and it becomes a solid, even though it's hot. The same thing happens with the core. You would expect the inside of the planet to be a higher state of matter, right? Like go from liquid to gas. But no, because of the pressure, instead of being a liquid or a gas, it's going to be all the elements pushed so close together, all that iron and nickel, pushed so close together that instead of being a liquid, it becomes a solid. All right, so let's see these layers next to each other, right? Here, I'm going to make sure again, because it's super important that this is still recording. I'm going to get more confident with this later. Whoa. All right, yeah, it's still recording, great. All right, so we've got the crust, chemical crust, the chemical mantle, and the chemical core. The lithosphere is made out of chemical crust, so it's got crust in here, and it's got a teeny tiny bit of the mantle in it. So chemically, the lithosphere is just solid crust and solid mantle. Then the next layer is all made out of mantle. The asthenosphere is made out of mantle, and it's acting like a liquid plastic. Up here we've got a solid. And remember, this is oxygen, silicon, and aluminum. This here is the oceanic crust. It's oxygen, silicon, iron, and magnesium. Oh, come on, let me write it. Magnesium. And then the mantle is the next chemistry down. And this chemistry for the entire mantle is oxygen, magnesium. I think it's silicon, iron. If I got that wrong, then I am sorry, but you can go back and check. Might be iron, silicon, but I think it's silicon, iron. And then we go down one more, and we've got the entire core is made out of iron and nickel. All right, so the asthenosphere is a liquid version of oxygen, magnesium, silicon, and iron, and the lower mantle is a solid version of oxygen, magnesium, silicon, and iron because of pressure, because the pressure is higher here. We go down and we get into the outer core. Outer core is made completely of iron and nickel, and it's a liquid. And then we get further into the inside of the earth. Pressure is increasing, and that iron and nickel is pushed so close together that it becomes a solid. All right, great. Moving on. Let's see this one more time. Here's the core of the earth. The inner core is a solid. The outer core is a liquid. Then we go to the mantle. The lower mantle is a solid. The upper mantle is that plastic liquid. And then we get to the crust. And the crust and that top of that mantle is our lithosphere. And the upper mantle is the asthenosphere. The crust and the very top of the mantle is the lithosphere, and it is solid. When it sits rigid in here, that means solid. All right, so back to this idea again. The earth is made it has layers. It has two different ways to describe those layers. One way is chemically, which is elements, and one way is mechanically or physically, which is states of matter. And one chemical or one set of elements can have more than one state of matter. And usually the state of matter in the earth is going to be controlled more by pressure. Pressure is controlling that state of matter instead of temperature. Let's look at this for one more idea on seeing the difference between these states of matter, right? So I've got a lot of heat and a lot of pressure. We've got strange mechanical or physical properties. So normally, more heat causes which of these to happen? If there's more heat, the atoms will move more, or the atoms will move less. Will they move more or move less? Normally, the atoms will move more, right? So in this case, this is a liquid. In this case, this is a solid. All right, and that's because of increasing temperature. As we increase temperature, we're going to change the state of matter from a solid, generally, to a liquid, to a gas, and then to plasma. But again, in this class, we don't care about plasma. All right, but in reality, if we increase the pressure, so this is high pressure, and this is low pressure here. If we increase the pressure, we can push those atoms closer together and move from a gas to a liquid, and then a liquid to a solid. And this is the main thing, the liquid moving, the atoms in a liquid being pushed together into being a solid. So states of matter can be controlled by temperature. Oh, you can't see that. Temperature or by pressure. Increasing temperature moves from solid to liquid to gas. Increasing pressure moves from gas to liquid to solid. All right, and little side note, this is just out of, if you've got curiosity about what this whole plastic thing means, the mantle is a non-Newtonian fluid like oobleck, and you can make your own oobleck. You can look this up on the internet. You need cornstarch, and I don't remember if I saw cornstarch in normal Mongolian stores, but I know that you can get cornstarch in American or import stores. So if you want to try this, you can go get some cornstarch. Whoa! Why did that happen? There we go. You can get some cornstarch, and then you can add a little water at a time and stir it together until it becomes the strange consistency. Stir it. It becomes the strange consistency where it acts like a solid when you're adding pressure, and it acts like a liquid when you're not adding pressure. And plastic means that viscosity, or the way that a substance flows, is dependent on shear stress. And that shear stress is deformation that's parallel to the stress that's being applied. You do not need to understand this for this class. I think it's very interesting. I think you should go learn about it on your own, but I'm not going to ask you about it. So if you're curious, go look that up. All right, one more last thing before I talk to you about the quizzes. The structure of the Earth is similar to structure of other planets and even stars. So let's look at an old star. I talked about an old star at the beginning of the class. An old large star will have burned through its hydrogen and helium, and it's going to start creating elements all the way up to iron. But iron is high density, so it's going to store that iron at the center of itself because of its density pulling it to the center of the star. Above that, we're going to have slightly less dense silicon and sulfur. And above that, less dense oxygen, neon, and sodium. And everything becomes lighter as we go to the outside, up to hydrogen and helium. So that's an old star. It has layers just like the Earth. And we know that other planets do as well. Mars has faults. We can see where there have been earthquakes in the past. That shows us that even though the outside of Mars is solid, at least at some point in the past, not now, we think it's solid all the way through now, but in the past it must have had a liquid mantle underneath the solid crust. Very interesting. All right, so how am I going to give you guys grades in this class? I haven't figured out testing yet. I'm going to figure that out in the future, but for your quizzes, what I want to do is just see from you what you've learned. And how we're going to do that is that each week you're going to make me videos to tell me what you understand, to show me and tell me. So you're going to stand together as a group in front of a whiteboard, and one at a time each of you will answer a question. So this week there are 4 sets of questions, 4 sections. That means you will make 4 videos. In each set of questions, in each section, there are 3 questions, and each student will answer 1 question. So you can choose which questions you want to answer. Maybe in the first section you answer question number 1, and the second section you answer question number 2, and then maybe another student answers question number 3, and then answers question number 1 in the second section. I'll show you how this works. So here's an example. First section, we're going to talk about history of the Earth and the elements all the way to a melted Earth. So maybe Tsoma wants to answer the first question. So she would stand up and explain how elements formed in stars. You can draw or talk, or you have to talk, but you can draw also if you want to. Then maybe Amka wants to answer the second question. This would be the history of how the Earth formed from, not just from minerals, but also from elements and minerals. So you'd take the second part and explain that. You could draw if you want to. And then maybe Ina likes the last question, so she wants to answer it. What made the earth hot enough to be completely melted? So you have to decide who's going to answer which questions. You can do them in different orders, but you each have to answer each of these questions. You have to in total, each answer a question to make the total video. So each choose which question you're going to answer in each section. Do it for each section. You're going to make one complete video for each section. This means you can't start and stop, start and stop, start and stop. You can't make 3 videos, one for each question, and then put them together in one section. No, I want one complete video that answers all 3 questions. All 3 students are going to talk on the one video, and you'll have 4 total videos this time. You'll get individual grades for your answer, but you also will get a group grade for your complete answer. This means that you need to talk together before you make your video to make sure everyone understands their answer. If you think that one of the students doesn't understand or is making a mistake, you can stop, talk to each other, and then make the video again. Make a whole new video. Don't cut and paste. Make one video from beginning to end with as complete and correct an answer as possible, but each student answering their part. During the videos, do not use notes. Don't read notes. Don't look at your notes or anything. I want you to answer from your own head. So you have to be ready, like a quiz, right? You wouldn't have notes during a quiz. And don't talk to one another while you're making the videos. Like I said, you can stop and correct each other and then make the video again, but you have to make sure you all understand and do the video from beginning to end without talking to each other and correcting each other during the video. So just talk to me in the video, just each of you, one at a time, talk to me. Tell me what you understand. You can use drawings. Sometimes you have to use drawings to explain everything. Make sure that the video is clear. And yeah, just do your best to answer the questions. I'm really wanting to see your face and see your eyes and see that you understand. As a teacher, me seeing you is a big part of me knowing if I can see if you understand or not. So this is why we're doing videos. Since I can't see you while I'm teaching you, I'm going to see you during quizzes. All right. And again, if you don't agree, stop, talk to each other, try it over again. All right, so your first videos, you're going to have 4 different videos, 4 sections. Each of you gets to pick. You don't have to Ina doesn't have to do all of number 1 and then Salma all of number 2. You can choose for each section who's going to answer what part. So for video 1, someone needs to tell me the history of how the elements formed in the stars. And then the next person needs to tell me how the earth formed, starting with elements and minerals. Elements, really, becoming minerals, and then minerals becoming rocks, right? And the third person needs to tell me what made the earth so hot that it was able to completely melt. It wasn't solid rock, it was liquid, so that it could sort itself into layers. How did that happen? Make that video, stop, and then start your next video. Your next video has drawing. You have to draw for this one. First student will tell me about convection of heat and how convection happens in the earth to make the earth cooler. The second student will tell about conduction of heat and how conduction happens in the earth to make the earth cooler. And the third student will talk about radiation of heat and how radiation of heat happens in the earth to make the earth cooler. You can keep your drawings all up on the same board. Can't have your drawings or your notes on the board when you're starting. You have to start with a white board. But since it's one video, one student can draw and explain convection, and then you can leave that drawing if it helps, and then next student can draw and explain conduction. Do whatever makes sense, okay? The third video, one student will explain why the earth was separated into different chemical layers. The next student will explain why the Earth was separated into physical layers. Why are these different physical layers? And the third student will explain why is the Earth's core solid and why is it strange that the Earth's core would be solid? This is actually section 4, not section 3. In the fourth video, the first student will explain and draw the chemical layers of the Earth. They'll label them, tell me what their names are, and then explain what those layers are, explain how they're different from each other. Remember, that's chemistry there, so the chemical layers. The second student will draw the physical layers of the Earth, the mechanical layers, label those layers, and explain what makes each of those layers different from one another. And the third student will compare the physical layers and the chemical layers of the Earth, show how they're related to each other. All right, y'all. Y'all is, how do we say you in plural in Texas? I probably will use a little bit of Texan gibberish with you. So, all right, so that's all that I have for you today. Do your best on this quiz. I'm going to send, my notes are coming to you a little late. I'm locked out of my computer until the morning. So I'm going to send you the notes. I've got some reading that could help you. So go ahead and read the 4 chapters of a book that I'm going to send to you. And watch the YouTube video that I sent. And then if you have questions, what should you do? Yes, email your box or message me or something. Contact me. I need to know if you're struggling to understand something. Work together, but each person needs to answer their own questions. And I look forward to seeing your answers. All right, have a great week, and I'll send you a new video next week. Bye. Oh, almost goodbye.